Good morning. In the last class, we concluded that two TTL outputs should not be shorted. Rather, to be more specific, two totem pole type of TTL outputs should never be shorted together. If we short the two such outputs, then what may happen?
So when the input of one such circuit will be 1 and the other will be 0, and if they are joined together in such condition, then a large current may flow through it, and in
Yeah,
spite of the resistor, there may be.
it will be more correct if you say that a continuously large current will start flowing.
Yes, sir. Yes, sir.
That continuously term is quite important.
Okay, sir.
Because when the output is switching for any specific TTL gate, then also a large current starts flowing, but that happens
Yes, sir.
for a very
For a
brief
very
period.
short time. Yes, sir.
Thank you. But there are certain requirements where we do need to short outputs. Let us explain that. 1 minute. Say I have one processor and several input devices, I1, I2, say I3. For simplicity, let us assume that the data that the individual inputs want to send to the processor are having a 2 bits. That means the data width is 2-bit wide. So I1 is sending 2-bit data, I2 is sending another 2-bit data, I3 is also trying to send another 2-bit data, but they are not sending them simultaneously. Whenever they are ready with certain data, they will be sending those information. But it is also not guaranteed that they won't send data simultaneously. They may or may not, doesn't matter. So in that case, it will be very simple if I connect two wires from I1 to the processor, two separate wires from I2 to processor, and two separate wires from I3 to processor. So in that case, there will be no problem. Whenever I1 is ready with the data, the processor can readily accept that. And there is no ambiguity, nothing, no problem is there. But the processor must, now it must have dedicated input lines for all these three input devices. So how many such dedicated pins are required for the processor?
6.
Six dedicated pins are now required. Now that was a very simple scenario. Now normally data may be having 16-bit width or 32-bit width, even it may have a 64-bit width. Moderately, let us assume that the data is having a 16-bit width. In that case, for all these three devices, how many dedicated pins should be there for the processor?
48.
48. So in case the number of input devices is more than 3, let it be some 10 or 20. So you can definitely imagine that there will be too much pin requirement from the processor if we go for this type of dedicated input lines for the processor. So instead, what is usually done, not usually, it is regularly done, that instead of sending dedicated lines from the input devices to the processor, in the system, there is one bus called the data bus. The concept of bus, I think I have explained earlier. Have I not? Have I explained the concept of bus earlier?
Yes, sir.
Yeah. The bus is basically a number of wires which contain a similar type of information. Whereas that means here the data bus is a set of wires which will contain similar information. What type of information? Data information. So if the width of the
So
data
can you
is
repeat that line once again?
here, the basically we are naming this as data bus because this data bus is also consisting of a bunch of wires where each wire is part of a particular information, and this complete information is actually one data. So this whole wires will be communicating one part of the data from one place to another place. So each wire will consist of one particular bit of the data. Okay. So this the width of this data bus, as the width of the data is 2 bits. So with the number of wires that will be present in the data bus will also be number of wires that will be there in the data bus will also be 2. So I have drawn explicitly those 2 wires instead of simply drawing the bus and then marking it as 2. I have explicitly drawn the 2 individual wires. Fine. Now what normally is done is each input device will be connected to the bus. Similarly, the processor will also be. So whenever one particular input device is ready for the data, it will place the data onto the data bus, and the processor will readily accept the data, whatever data is present in the inside the data bus. That will accept, the processor will accept the data and act accordingly. Now there are 3 or 4 or n number of input devices. Now from which input device the processor is selecting data, how will that be decided? From which input device the data, the processor needs data from which input device, that how that concept is built or implemented. This also I have explained earlier.
Decoder diye.
Decoder.
Not decoder, not decoder. Before that, you have to give one specific address. That means there will be one address bus also. That address bus will be going to each of the input devices. Now, each input device will be equipped with one decoder. And for each individual input device, there is one dedicated address. So whenever that particular address is available, the input device gets activated. Same is true for the output handling with the output device also. There also that same address bus will be there, same data bus will be there, but there the thing is that the output device will accept data from the data bus. They will not send data to the data bus. They will just receive data from the data bus. That's the only difference between the input device and the output device. But the same set of data bus, same set of address bus will be there present in the whole system. In fact, when you will be starting microprocessor or microcontroller, you will see that internal to that microprocessor or microcontroller, there will be one data bus, there will be one address bus, and definitely there will be another bus that is called the control bus. The purpose of the control bus is apply common sense. Purpose of the control bus should be, if we apply your common sense, so what should be your answer?
Sir, to enable one input or not, I mean, I1 will come or not?
Fine, but can you be more specific?
So at what time when the
Yes.
processor will execute.
Just consider on the name. Here the name is data bus. So what is the purpose of this data bus? To communicate data from one place to another place. Here the name is address bus. Consider on this term address. So what is the purpose of this address bus?
Communicate the address of the data.
Communicate address from one place to another place. Similarly, if there is something called control bus, what will be the purpose of this control bus?
To shift control.
Yeah, no, not exactly.
To control communication.
Control signals, to send control signals from one place to another place. The data bus is sending data information of the data signals from one place to another place. Address bus is transmitting or sending or communicating address signals from one place to another place. Similarly, control bus will also be there to communicate control signals from one place to another place. What type of control signal? Now, when I am having one input device and I am having one output device, what is the basic difference between these two? Input device and output device? The processor will read data from the input device, whereas while communicating with the output device, the processor will write data onto the output device. So the processor needs to send one input read signal to the input device and one signal to the output device. So that read signal and write signal, that basically distinguishes between the input device and the output device. If the device receives read signal, that is basically one input device. If the device receives write signal from the processor, that device is basically one output device, because the processor is writing data onto that output device. So that's why it is getting the write signal. Okay, fine. Now, what the processor will first do is, it will just transmit or load one address onto the address bus. What will happen is, either this address bus will individually will go to all the IO devices, or it will simply go to one decoder. Normally what happens is, all the IO devices are equipped with internal decoding system. So in that case, there is no need to go for one explicit decoder inside the system, because I can now simply transfer the address information to the input, each of the input devices and output devices as well. Now, depending on the address, there is one internal decoder. That internal decoder will decode that address, and accordingly it will generate the output signals. If there is 2 bits in the address, how many output signals will be there in that internal decoder?
4.
4. So out of those 4, one particular output will go to its enable input. Say its address is 00. This I1 is supposed to be selected with the address 00. This output is supposed to be selected with 01. This is with 10. This is with 11. I have 4 IO devices, so 4 address is enough. So when the address is 00, this I1 will be enabled. When the address is 01, this will be output device will be enabled. When it is 10, this fellow will be enabled, and when it is 11, this fellow will be enabled. Now this processor will load a particular address, say 10. In that case, which input device is getting activated? I2. This 10 is coming here, as well as here, as well as here. So the output corresponding to 10 pattern will be enabled in all 4 decoder outputs. But as this I1 is enabled by the 00 output, So 0 0 output means my outputs are F3, F2, F1, and F0 of the decoder. Now, as this enable input is connected with the F0, as this enable input is connected with F1, this is F2, and this is F3 of the corresponding decoder. So what will happen is now my F2 is 1, F0, F1, F3, all three are 0. So this is disabled, this is disabled, this is disabled, but only this fellow is enabled. Now the processor needs to send one read signal to the input device I2. Rather, that read signal may go to everywhere. But as this is the one which is only enabled, data will be read from this particular input device I2.
স্যার বলছি এফ সিগন্যালটাই কি কন্ট্রোল সিগন্যাল এফ
আমার কি প্রত্যেকটা আউটপুটেই ডিকোডারের আউটপুটে 4টে করে সিগন্যাল রয়েছে।
হ্যাঁ
না, এই প্রত্যেকটা আউটপুটকেই আমি নাম দিচ্ছি F2, F3, F2, F1, F0, F3, F2, F1, F0, F3, F2, F1, F0, F3, F2, F1, F0. Now, এই যে 4টে set of outputs of the decoder, that F0 is going to the corresponding enable input of this I1.
ওকে
এখানে F1 টা যাচ্ছে corresponding enable input-এ, এখানে F2 টা যে corresponding enable, এখানে F3 যে corresponding enable input-এ। Okay, আমরা এটা করছি কেন? Because all the IO devices supposed to be having internal decoder.
আচ্ছা আচ্ছা
এবার সেই ইন্টারনাল ডিকোডিং ফ্যাসিলিটি না থাকে, তখন আমি কি করবো? আমার এখানে ডিকোডার অ্যাড্রেস বাসটা চলে যাবে একটা ডিকোডার, অ্যাড্রেস বাস চলে যাবে একটা ডিকোডার, সেখান থেকে আমার 4টে আউটপুট তৈরি হবে। এই 4টে আউটপুটকে এখন আমার ওয়্যার করে এই এনেবল ইনপুটে, এই এনেবল ইনপুটে, এই এনেবল ইনপুটে, আদার ইনপুটে লাগাতে হবে। So দুভাবে করা যেতে পারে, either taking help of the external decoder, or if the IO devices are equipped with the internal decoder, in that case we can take help of that also. তাতে কি হবে? আমার এখানে যদি আমার ধরো if the address bus is of with 16 bit, so corresponding decoder output কতগুলো হবে? If the address bus is having width 16 bit, in that case decoder output কত বিটের হবে?
2 to the power 16.
16, that means 64 kilo, 64k, 65,000 something. কতগুলো ওয়্যার কিন্তু আমাকে তাহলে ওয়্যারিং করতে হবে। So that is too difficult one. So it is always preferred that we take help of the internal decoding facilities of the IO devices. Okay, if that is available, fine. So now on getting the read pulse, the input device I2 will place the data onto the data bus. So this I2 will be placing data here as well as here. Now what will happen to the other two input devices, I1 and I3? What information will you be getting here as well as here? They are not enabled. This I1, is it enabled?
No, sir.
I3, is it enabled?
No, sir.
So their output, so what will be their output be?
Don't care.
Don't care means that may be 0, that may be 1.
yes sir
So let us assume they are having 0 output. Okay, now what does it mean? This wire, this is one wire, this data bus. There are 2 wires in the data bus. This I1 output device is connected to this data bus. This I2 is also connected to the data bus. Now, the wire means what? What is the impedance between two terminals of one wire?
0.
0. So, if I connect this output of I1 to this particular wire, that means with this output, this wire is shorted. Similarly, with this output, this particular wire is shorted, is not. If I say I have connected to this wire and this output to this particular data wire, same is true here. This is shorted, this is also shorted. This is shorted, this is also shorted. Now, what happens to this particular output, this particular output, and this particular output? Are they shorted or not? These three outputs of the three different input devices?
Yes, sir.
So they are shorted because they are shorted with the through this particular wire of the data bus. Same is true here. This wire, this wire, this wire, they are shorted through this data bus. So what I find is this particular output of input I1, this particular output of input I2, this particular output of input device I3 are shorted. Same is true for the other output terminals of the individual input devices also. So there, whenever we go for bus connection, this type of output shorting is a basic requirement. But if I take here, if my internal input devices are, the internal circuits are all developed with the help of TTL logic families, in that case, we know that the two totem-pole TTL outputs can never be shorted together. But here there is a basic requirement of output shorting. So definitely there will be a chance that in case this input device tries to place a logic 1 and this input device tries to place a logic 0, then this wire or this set of outputs will not get damaged, but this will get damaged. This. Is it not? Because this is trying to place a logic 1 and these two outputs are trying to place logic 0. So once again, that continuous current flow of continuous large current flow will start flowing through this particular output and these two particular outputs. So what will happen? Eventually the outputs will get damaged. But if we have to go for bus connection, we do have to go for shorting of outputs. So problem ta bujhte parlo? There is a requirement of output shorting, but using totem-pole TTL logic families, we cannot short outputs. Is this problem clear?
Yes, sir.
Yes,
Fine.
sir.
Now let us go for one thing. Say, forget about the processor. Let us concentrate on the input devices. I'm not drawing the processor. That is there. Definitely that is there. Now, when the processor wants to input data from I2, so it will be definitely sending the corresponding enable address for the address. It will be through the address bus. It will be transferring the corresponding address of I2 to the address decoder. Accordingly, this I2 will be enabled and I1 will remain disabled. Now, earlier we thought that if one input device is disabled, it may place don't care output. We assume that don't care term to be placing 0 output. If it is 1, then also some sort of problem will, similar sort of problem will be there. Now say I2 is enabled and this is disabled. Now, if I can introduce one particular output state, which is neither 0 nor 1, rather, if I say that this input device I1 is disabled, if I can disconnect these two wires from the data bus, if we can disconnect the two outputs of I1 from the data bus, then will there be any sort of problem?
No, sir.
Because that is electrically isolated. The removing connection means these two outputs of I1 are electrically isolated from the two wires of the data bus.
So only
in
when
other words-
I2 is enabled.
Bolo, आगे बोलो.
So only when I2 is enabled, right?
Only when I2 is enabled, and if I2 is remember that address bus will contain only one particular address,
Yes, sir, yes.
and the address is specific for every device. So if I place the address corresponding to I2, that means I1, I3, I5, I4, I10, I100, everything is disabled. Only I2 is enabled. So what my requirement is that the input devices which are disabled, which are supposed to be disabled, they should be forced to electrically isolate their outputs from the wire, from the data bus wire. If I can do that, in that case, there will absolutely be no problem of the shorting of electrically shorting of the outputs. Is it not?
Yes, sir.
That means at a time then only one set of output of one particular input device will be electrically shorted to the data bus. The others are electrically isolated. Now, what do you mean by electrical isolation? If I say that this particular output is electrically isolated from this particular wire, what will be the impedance between these two?
Almost infinite.
Yeah, almost infinite, or to be more specifically, infinite, you can say. Okay, so that means now we have to try to ensure that in case the output of one particular TTL gate is supposed to be disabled or electrically isolated from the external world, it should be posing infinite impedance to the external world. So now there is a requirement that the output of one TTL gate, TTL totem pole output, should be having three states. One is the logic 0 state, one is the logic 1 state, and the third one, the new one, is high impedance state. When the output is driven to the high impedance state, it is basically electrically isolated from the external world. Okay, so is this requirement clear?
সে একবার রিপিট করবেন
When that means what I require is, in case one input device is supposed to be disabled, its output should electrically isolate from the two data wire, to data, the individual wires of the data bus. Its output should electrically isolate itself from this. Now, electrical isolation means it must place infinite impedance to the external world. If one node places infinite impedance to the external world, that means I can say that this particular node is electrically isolated from the external world. Okay, so now normally we know that all internal circuit components are developed using TTL gates, and if you are talking about TTL logic gates, that means the output will invariably be totem pole type of output, so that the propagation delay type of problems does not arise. So the output is totem pole type of TTL output. So normally it will be having only logic 0 and logic 1 output states. But here I do have another requirement that there should be introduced one third possible state apart from logic 0 state and logic 1 state. And in the third state, when it will enter into the start state, now when this device is supposed to be disabled, when that device is supposed to be disabled, it should only enter into the third state, and that third state is electrically isolated from the external world state, and that means here the output will place infinite impedance to the external world. So that means the output gets electrically isolated from the external world. When that happens, now when this particular output device needs to be isolated from the external world, needs to be disabled from the external world. Otherwise, this output will be having only logic 0 state and logic 1 state. Only when this output device needs to be disabled from the external world, then only it should place infinite impedance to the external world. Is it clear now?
Yes, sir.
Yes, sir.
Now let us see how that can be implemented in the case of TTL. The extra addition is this diode D1. In case Z is 1, tell me how is F related to A? When Z is 1, how will F be related to A?
A bar.
Let us see what others say.
Sir, A bar.
In case A is 0, what happens to Q1?
Normal mode.
Normal.
If it is normal mode, that means the current is trying to move away from the base of Q2. So Q2 will be off. Naturally, Q3 will be off. And as Q3 is off, Q2 is off, my Q4 is on, and the output is logic 1. In case this is logic 1, in that case, Q1 and as Z is also 1, that means both the base emitter junctions are reversed biased. So Q1 will operate in inverse mode. So as a result, Q2 is getting base drive. So Q2 will be on, Q3 will be on, and we can definitely establish that Q4 will be off. So the output will be logic 0. So in case Z is 1, F is equal to A bar. Now let us make Z is equal to 0. In case Z is 0, what happens to diode D1?
Forward bias.
This is on. What happens to Q1?
Normal mode.
Normal mode. As it is operating in normal mode, will Q2 get any base drive?
No.
No, sir.
So Q2 is off. As Q2 is off, can Q3 be on?
No, sir.
Q3 is also off. Now, Z is logic 0. So voltage level wise, let us assume that to be 0 volt. So what will be this potential? Approximately
0.6.
0.6. So what will be this potential?
0.6.
0.6. So will this 0.6 volt be sufficient to turn these two junctions on?
No, sir.
No, sir.
So this will also be off. So from this particular terminal, from this particular terminal to this side, how much impedance you are getting?
Infinite.
In this side, how much impedance you are getting?
Infinite.
So this node, this output node is placing infinite impedance to the external world. So that means from this side, from this external side, if I try to observe what is the impedance this particular output node is placing, what I find? The net impedance is nothing but infinite impedance. Is it not?
Yes, sir.
What about others? Confusion থাকলে বলো.
No, sir.
Fine. So that means in case Z is equal to 0, irrespective of the condition of A, there is a condition of A does not matter. In case Z is 0, what happens? The output enters into that particular specific third state where the output node places infinite impedance to the external world. So the TTL gate, this TTL output basically enters into that third state. There is the high impedance state or infinite impedance state. Okay. So this concept can be readily used in that bus connection. Now, in case I2 is enabled and I1, I3 are disabled, that means here the how the circuit will be implemented is at the final output. Here I will be getting two such totem pole outputs. Internally, definitely there will be one complex logic, but I am not bothered about that. Now, when the input device is ready, it is ready with certain data. So that data is available here at the input place. But at the last stage, I am having one particular type of TTL logic which follows this type of concept. In fact, this particular TTL logic family is called tri-state TTL logic. The other previously whatever TTL circuits you have seen, they are the standard TTL logic families. When inside the TTL logic circuit, we implement this diode D1 and make the connections accordingly. In that case, that particular TTL circuit is called one tri-stated TTL. Here, specifically, this particular circuit is called one tri-stated TTL inverter. This is called one tri-stated TTL inverter. In absence of this, that will be one 2-input TTL NAND gate, standard TTL NAND gate. But if this diode is fabricated inside the IC, in that case, that will be no longer your 2-input TTL NAND gate. This should be now one tri-stated TTL inverter. We can implement TTL NOR gate, we can TTL AND gate, we can implement TTL NAND gate, everything we can implement. But whatever you have to use in the bus connection, there, internal to the circuit, you go for the standard TTL logic family. But when the final output is prepared, and before transferring that to the bus, the data bus, you pass it through one set of tri-stated TTL, where there will be one enable input. This enable input is basically coming from the address decoded output, the address decoder output. If this particular input device is supposed to be enabled for data transfer, this enable will be 1. If this is not supposed to be enabled for the data transfer, the enable will be 0. Now this enable input is your Z signal of the tri-stated TTL inverter. This enable input is basically coming here. If that enable input is 1, that means now this will the output of this TTL will be either logic 0 or logic 1. But if this enable is 0, in that case this will be high impedance state Z. Don't confuse with this impedance Z and this signal Z. They are two different things.
So can you please explain the last part again?
Yeah, sure. So what we're trying to do is, here, say this is my input device I1. Okay, definitely some complex logic circuit is there, which is dealing with the requirement of the particular data that needs to be transferred. So after processing, lot of processing, it is ready with the data, and the 2-bit data is as if these are the 2-bit lines. But I am not, or the input device I1 is not sending this 2-bit data as it is to the data bus. Here, these 2 lines are actually getting connected to the data bus. What we'll be doing is, here one tri-stated TTL inverter is there, and a tri-stated TTL inverter is there. It is having one enable input, it is also having the same enable input. Now, if this enable input is 1, that means its output will be either logic 0 or 1. Similarly, if this enable input is 1, this output will be either logic 0 or 1. Whereas if the enable input is 0, in that case, both will be isolated. This will be high impedance state. The output will attain high impedance state. So that means electrically that output will get isolated from the external world. That means now with this output, there is no electrical connection between this output and this particular data wire. not this output with this particular data wire. And I know that if there are 4 input devices, only one input device will get enable input 1. The other 3 input devices will get enable input 0. So for those 3, these corresponding final output stage will isolate themselves from the external world. Now only that particular input device which is getting the enable input 1, there as internal to the final stage tri-state TTL logic family is getting Z is equal to 1 or enable is equal to 1, the corresponding output will be a valid logic 0 or valid logic 1. So that electrical signal will actually get transferred to the data bus wires, individual wires. But that will happen for only one particular input device, because by placing the proper address, I am ensuring that only one input device gets enabled. The other input devices are remaining in disabled condition. So there, the final stage outputs will be electrically isolated, whereas only one input device, it will make sure that its output is electrically one viable data, and it will place that data onto the data bus. Now tell me what is the problem. If there is any confusion.
Sir, tri-stated data কি মানে ওর ভেতরেই করা আছে এনকোড, মানে ওই আইসিটার ভেতরে?
Either internal to the device there is one address decoder, or externally আমার address decoder আছে,
আচ্ছা,
যার এই যে আউটপুট গুলো, এনেবল আউটপুট গুলো, সেগুলো একটা ইন্ডিভিজুয়াল ডিভাইসে যাচ্ছে। ধরো এটা যদি আমার F2 দিয়ে যে এনেবলড হয়, এখানে হচ্ছে ধরো F0, F1, F2, F3. So this F2 will come here.
আচ্ছা আচ্ছা,
বা এটা যে ইন্টারনাল ডিকোডার হয়, এখান থেকে আবার F2 এখানে।
আচ্ছা,
So ওই অ্যাড্রেস ডিকোড করে আমার যে আউটপুটটা পাচ্ছি, that output will actually go as the Z input of the tri-state logic. Z input or enable input, whatever you may term. আর কোনো? না থাকলে আমি পরের টপিকে চলে যাব। Any confusion? Any other confusion?
No, sir.
No, sir.
Fine. Thank you. Some of you might have handled the TTL NAND gates. What is the part number of that? The latter entry students? Tomal or somebody?
नहीं sir, क्यों?
Acha, fine. So when you will be going to the lab, you will be or handling with the ICs of digital logic families, you will find that that the TTL logic gates, they are starting with their part number starts with either 574 or 54. Now this 7, whenever you and before that there will be something else. So that basically comes from the company which is fabricating that particular device. So I'm not bothered about that. So these alphabets will basically correspond to one individual company, that is Motorola, whether it is Motorola or Texas, there are many other companies which fabricate the device. But it will, by seeing whether it is 74 or 54, I'll readily say that it is one TTL logic gate. Now, what is the difference between 74 and 54? The 74 is the commercial grade ICs, whereas 54 is the military grade IC. Definitely, the 54 series ICs are not readily available in the open market. We have to take special permission for their procurement, and they are definitely much more costlier as compared to the 7-4 series. These 5-4 series military-grade ICs, they are more rugged. For example, in 7-4 series, it may, my VCC level is 5 volt, it may tolerate plus minus 0.25 volt jitter. That means the supply voltage may range from 4.75 to 5.25. But when you go for the military grade 5-4 series IC, that is 5 volt plus minus 0.5. So wider fluctuations can be handled by the 5-4 series IC. Similarly, there is one temperature range. There is within this temperature range, this particular IC can be used. If you go for 5-4 series ICs, they can handle much wider temperature range. Because in the space or in very adverse conditions, the military grade ICs, military grade systems are to be designed. So there the ICs should be much more rugged. Now this NNN, they basically identify one particular device, one particular logic gate. For example, if the NNN value is 00, that means 7400, that is basically quad 2 input NAND. That means inside 17400, I have 4 numbers of 2 input NAND gates. So for 4 numbers of 2 input NAND gates, how many IO pins are there?
12.
12. Apart from that, one VCC and one ground terminal will be there. That means this is basically one 14-pin IC. The 7400 is a 14-pin IC where I have one specific VCC line, one specific ground line, and 8 input lines and 4 output lines.
স্যার নামটা এরকম কেন 7400?
Oh, that I don't know. There are thousands of such logic devices, and whenever somebody fabricates a new one, he gives a new number. That's all.
Oh,
In fact, that this 00 corresponds to one quad 2 input NAND gate, that you can only verify through the after consulting the data sheet.
ও মানে কোনো নোমেনক্লেচার নেই?
No, সেরকম কিচ্ছু নেই।
আচ্ছা আচ্ছা।
ইনফ্যাক্ট তোমার ধরো একটা রিকোয়ারমেন্ট হয়েছে একটা 4 to 16 লাইন ডিকোডার, সেটা লাগবে তোমার। কি করব আমি? ডাটা শিট সার্চ করব, সেখানে ডিকোডারের মধ্যে গিয়ে দেখবো যে 4 to 16 লাইন কোন ডিকোডার আছে কিনা, থাকলে তার পার্ট নাম্বারটা সেখান থেকে খুঁজে বের করবো ডাটা শিট থেকে। ওখানে ইন্ডেক্স থাকবে, সেই ইন্ডেক্স দেখে আমার করতে হবে। আর এখন তো ডাটা শিটও দেখার দরকার পড়ে না, কারণ গুগলে সার্চ দিলেই বেরিয়ে আসবে, সব ডাটা শিট গুগলে পাওয়া যায়। ফর এক্সাম্পল যেমন 74138, দ্যাট ইজ 3 to 8 লাইন ডিকোডার। 7476, dual JK master slave. 7476 is dual JK master slave. So there is hundreds of thousands of such devices. So as per your requirement, you have to search the data sheet to find out what is the part number. Accordingly, you have to go to the market and purchase that. Fine. Now before this 00 and this, between the 74 and 00, you'll find that few alphabets might be there in between. What are their significances? Let me go for that. This was my standard TTL 2-input NAND gate. Now, if I increase these resistance, what will happen? If I increase the values of this resistance, what will happen? The net current that will be flowing from VCC to ground through this Q2 or through any transistor will be reduced. That current will, when that current will flow, when that corresponding device is on, then only the current will flow. Is it not?
Yes, sir.
So if I increase this individual resistances, what will happen is the net current that will be flowing through the device when that is on, it will be reduced.
Yes,
Sure.
sir.
Now, if the current through the device gets reduced, what will happen? The power dissipation across the device will be reduced.
Yes, sir.
But there, what problem you will be facing in turn?
On off होते बेसी delay लग
Delayed बढ़ जाएगा. The switching time will get hampered of the device. So there is a particular requirement where I need my circuit as one low power device, that is low power dissipation device. So there it is 74L00. Why low? How can we achieve the low power dissipation? By increasing the resistance values. But this 74L00, this device will have one compromised propagation delay, because propagation delay will be much higher as compared to the standard 7400. So as compared to the standard 7400, this 74L00, that will be having much worse propagation delay. But the advantage of a 74L00 is the power dissipation will be less. Now, if I reduce the resistance values, can you predict any advantage of that? If you reduce the resistance values?
So reduced propagation delay.
Yeah, that will lead to a reduced propagation delay. So that is another family of TTL logic gate, that is 74H00. Here the H stands for the higher speed of operation. So the speed of operation of the NAND gate will be increased if I reduce the resistance values. But what will be the disadvantage there?
The more power dissipation.
The current that will be flowing through the individual devices will be more.
Yes, sir.
So as a result, the power dissipation will also be more. So ki dekhlam? If I try to go for reduced power dissipation, my propagation delay is getting compromised. Whereas if I try to improve the propagation delay as compared to the standard TTL logic, my power dissipation is getting compromised. So, but there will be one particular type of requirement where I can have, I want to have a better propagation delay. At the same time, my power dissipation should not get compromised. That means my power dissipation is also improved. Improved means I should go for one lesser amount of power dissipation, and at the same time, my propagation delay is also becoming better. Let us see what can I do for that. What is this device?
Diode.
What type of diode?
So Zen diode.
What is this diode?
Zener.
Zener diode.
What is this?
So Schottky.
অভিরূপ
The Schottky diode.
স্কচকি নয় বাবা, ও তো খুব
হ্যাঁ, স্যার,
স্কচ
মুখটাই
খেয়ে
বেরোচ্ছে।
স্কচকি বেরিয়ে গেছে। ও তো স্কচ খেও না। So this is basically one Schottky diode. Schottky diode. What is this? এটা কিভাবে fabricated হয়? Is there any PN junction here?
No.
It's basically one metal semiconductor junction. What is the advantage of this Schottky diode? What is the cut-in potential of this Schottky diode? Have you ever read this Schottky diode? In
Yes,
first
sir.
year? Fine, good. What is the approximate cut-in potential of the Schottky diode?
Point 2.
Yeah, it's 0.1 to 0.2. And the thing is here, the switching speed is quite fast because as there is no depletion region involved here, and there is no such your charge accumulation type of concept is present here. So the switching speed wise, the Schottky diodes are pretty fast. And the more convenient thing here in our case is its cut-in potential is very small, around 0.1 to 0.2. Now, in our TTL logic gate circuit, how many, in this specific circuit, how many transistors are there?
4.
4. Out of which Q1 operates in
Normal or inverse.
either normal mode or inverse mode. It is not operating in the switching mode. But the other three, Q2, Q3, and Q4, they are operating in switching mode. That is either they'll be on or they'll be off. So when a transistor is on, that means it's saturated. What happens to the base emitter and base collector junctions? When
Forward
one-
bias.
So both are forward biased.
Both are forward biased. Fine, very good. Now let me come here once again. This is say my any particular say Q2. This is that Q2. If this is forward biased, that means this will be plus minus around 0.6 and this will be plus minus around 0.6. So truly speaking, this will be around your VC is
Operate to 0.4.
0.4 এর মতো হবে। Fine. That means this will be less forward biased as compared to the base emitter junction. Now, if I introduce one Schottky diode between the base and the collector, when I try to turn Q2 on, this will be plus minus 0.6. There is no confusion in that. But can you get plus minus 0.4 here? Between the base and the collector?
No, sir.
Because just after the voltage rises above 0.1 or 0.2, this will be turned on.
Yes, sir.
So what will happen is between these two terminals, the maximum voltage that you can have is around 0.2. Even it can maybe less than that. If the cutting potential is less than 0.2, that will be clamped to that particular 0.1 or 0.2 volt. So this base collector junction is never completely forward biased. As a result, this Q2, this particular transistor will never be hard, will never enter hard saturation range. As it is not completely saturated or completely on, what will happen is when a transistor is saturated, what happens is there is one large amount of charge accumulation in the base region. Now from that on state to when I want to bring the transistor to the off state, first that accumulated excess carriers in the base region needs to flow out, and then only it can enter, go through the active region and enter into the cutoff region. So while removing that accumulated excess carriers within the base region, some finite time lapses. So if we can ensure that there is no such excess carrier accumulation within the base region, in that case that time can be saved. So my switching speed will greatly improve if there is no excess carrier accumulation within the base region. And that's what is ensured if we can introduce one such a Schottky diode between the base and the collector of this transistor. In that case, as the base collector potential never can rise above the 0.2 volt, this transistor is never hard saturated. So excess carrier accumulation will never be there. So very quickly, the transistor can be turned off from the on condition. So switching speed is greatly improved. So that means my sorry. That means my overall propagation delay of this particular TTL gate will be greatly improved if we can replace all the Q2, Q3 and Q4, all these three, by corresponding one Schottky transistor. Remember, I have not told you, this configuration is called one Schottky transistor, and its circuit symbol is this is the circuit symbol of the Schottky transistor. Basically, by Schottky transistor, what I mean is there internal to the transistor, during fabrication of the transistor, one Schottky diode has been fabricated between the base and the collector. If the transistor is fabricated in that form, that means one standard NPN transistor is fabricated. Along with that, between the base and the collector, one Schottky diode is also fabricated. So if that is the configuration of that particular transistor, if that is the way the transistor has been fabricated, in that case the resulting transistor will be called one Schottky transistor, and its circuit symbol will be like this. Okay, is it clear?
Yes, sir.
Yes, sir.
So now here, if I replace this transistor Q2 by one Schottky transistor, Q3 by one Schottky transistor, and Q4 also by one Schottky transistor, in that case I can ensure that the propagation delay involved in this transistor, in this TTL gate, will be greatly improved. Now, as I am improving the propagation delay by introducing Schottky transistor in place of the standard switching transistors, now I can readily increase the resistance values so that the power dissipation inside the devices can be reduced. That means I am increasing the resistance values to reduce the power dissipation inside the device. But if I go for increasing the resistance values, what I have earlier seen, the propagation delay will be compromised. the propagation delay will be worse. But now, to improve the propagation delay, we have replaced the switching devices by the Schottky devices, Schottky transistors. So by introducing Schottky transistor, I have improved the propagation delay. And at the same time, by increasing the resistances, I am improving the power handling capability of the transistor, or of the TTL gate. That means the TTL gate can now operate at a much lower, with lower power dissipation. So that particular series of TTL gate, where I introduce Schottky transistor as well as I increase resistances to reduce the power dissipation into the TTL gate, that is called 74LSNNN. This L stands for the low power device. Low power device, how we are ensuring that?
So by
The
increasing
resistance.
And this S stands for, this is a Schottky. The switching devices are now Schottky transistors. So this 74LS basically stands for 74 low power Schottky. Then this is the part number 001387674, whatever it is, 0604. Okay, and in our laboratory, what you will find, or if you go for the purchasing any device in the Madden Street, you will find that most of the TTL gates are 74LS type. So that is the mostly used type of 74 series that we have in our laboratory, and that is also mostly available in the market also. Now I'll introduce a few more terms. VIL max. What does it mean? Now, the input signal, I am getting one input signal. This is the maximum input signal strength that will be treated to be logic 0. VIL max stands for the maximum input signal strength that will be treated to be one logic 0 input. Is it clear, or I'll repeat?
It's clear, sir.
VIL max stands for the maximum input signal strength that will be treated to be one logic 0 input. When I am inputting one signal, if the signal is less, then there is no problem. But if the signal is very large, is wide apart from the logic 0 voltage, in that case, that may create a problem. Normally, what you do? This is your 0 volt and this is your 5 volt. So VIL max means I am ensuring that my up to this voltage level, I will be treating that to be 0. So definitely, if the input voltage is somewhere here, that will also be treated to be logic 0. But I cannot guarantee that the input will be treated to be logic 0 if it is above this. Okay, is it clear now? This VIL max is this particular level. So this is the voltage level, which signifies that below this, everything less than equal to this input signal, I'll be treating that to be 0. But if the signal is above this, I am not. I cannot say about whether this is 0 or not. But rather, I will say that this is not 0. Clear?
Yes, sir.
Now VOL max. VO stands for, it is outputting one signal level. So while outputting one logic 0 signal, the device is ensuring that the output signal will be maximum this much. So once again, I'll be having two levels. So the device ensures that while the device is outputting a logic 0 signal or logic low signal, the signal strength will be somewhere there. It will not go beyond this VOL max. The output signal strength will never be greater than VOL max when it is outputting a logic low signal. Clear?
Yes, sir.
Now tell me one thing. Out of these two, VIL max and VOL max, which one should be higher, or should it be should there be one requirement that both should be same? There may be three situations. VIL max and VOL max should be same. VIL max should be higher than VOL max, or VIL max should be lower than VOL max. Now tell me, out of these three situations, which one is preferred and why?
So VIL max should be higher.
Why?
So because when the device is taking input signal, there may be error. So if VIL max is
What type of
more,
error? What type of error can be?
so
What is the source of that error? What might be the source of the error?
Positive noise.
Noise signal.
noise signal, yes, sir.
Okay.
So-
So for TTL logic family, this VOL max is 0.4 volt. VIL max is 0.8 volt. So that means while outputting one signal, logic low signal, the signal strength may be 0 volt, maybe 0.0001 volt, or it may go up to 0.4 volt. That is the 0.4 volt is the maximum signal strength that may be there at the output. Now, if during transmission, if there is negative noise, there will be absolutely no problem. The received signal strength will be less than 0.4 volt. Is it not?
Yes.
If the received noise is of a negative nature, in that case, the received signal strength will be less than 0.4 volt. But if the noise, added noise is of positive nature, then the signal strength may be more than 0.4 volt. We have to take account of that. So if we have to give some allowance for that type of noise, positive noise, we have to ensure that VIL max should be higher, magnitude is higher than the VOL max, so that certain amount of positive noise can be accommodated. Okay, how much positive noise can be handled here without any giving any problem?
0.4 volt.
0.4 volt. So the noise margin under logic 0 condition is 0.4 volt or 400 millivolt. Okay, two more terms will be there. VIL mean and VOL mean. Can you tell me what they signify? What about VIL mean? Apply common sense and try to say.
মিনিমাম ভ্যালু অফ ইনপুট যাতে সেটা লজিক 1 কনসিডার হয়।
Sorry. I have made a mistake. This should be VIH mean and VOH mean. Sorry. Extremely sorry. Go ahead.
Sir, VIH min can be maximum input signal.
No,
No,
not
sorry,
maximum. No.
minimum input signal strength
Minimum
that
input
would be
signal, yes.
treated as
When you are trying to input a logic 1 signal, you are more concerned about the lower level,
yes, sir.
not the higher level.
Yes,
The
sir.
higher the signal strength, it is better. But
Yes.
if it is lower a certain level, then there may be some problem in detection of that signal strength. So there, we basically, while handling with the logic high signal, we are basically concerned about the lower minimum levels. So VIH mean is the minimum input signal strength that will be treated to be logic high. The input signal strength, the minimum level of it, which will be still treated to be logic high. But below that, I am not sure about the signal strength. What I am sure is it is not logic high. I cannot readily say that this is logic high, but what I can say is this is not within my range, so I'll presume that this is not logic high signal strength. If it is below that, if it is above this minimum strength level, then I'll readily accept that to be logic high. Similarly, VOH mean is the same thing with reference to the output signal.
Sir,
Here,
sir,
minimum guaranteed output signal strength under logic high condition. Under logic, while outputting a logic high signal, what is the minimum guaranteed output? So now once again tell me, out of these two, which one should be higher and why?
VOH.
VOH should be higher because when you are inputting logic 1 signal, there the negative noise is of importance, not the positive noise. So to accommodate certain allowance for the negative noise, I must ensure that my VIH mean is less than VOH mean. And for TTL logic family, this is 2.0 volt, this is 2.4 volt. That means while inputting one input signal, if the signal strength is more than greater than equal to 2.0, that signal will be treated to be logic 1. While inputting one logic low signal, if the signal strength is below 0.8 volt or less than equal to 0.8 volt to be more specific, that will be treated to be logic 0. So under logic high condition, what is the noise margin?
0.4 volt.
Once again, 400 millivolt or 0.4 volt. So in the case of TTL logic families, the noise margin is not very large. It is of the order of 400 millivolt or 0.4 volt. Now you may raise one question that, sir, if the input signal strength is within 0.8 to 0.4, within 0.8 to 2.0, what will happen? What will be the inference? Here, the inference is it cannot be detecting one valid signal strength. It may respond in some arbitrary manner. Nobody knows what will be the response of that particular signal. So if the input receive signal is within that 0.8 to 2.0 volt, the response is not guaranteed. Nobody can predict what will be the response. Okay, fine. Another term. Fan out. Fan out specifies the maximum number of loads that can be connected to one particular output line. I have one output node, one TTL NAND gate is having one particular output line, that F output line. So that output, from this output, how many loads can be connected? How many standard loads can be connected without degrading the performance of the output? say this is my output. This might be connecting this might be going to two inputs of two different NAND gates. It may so happen. It may go to inputs of n different NAND gates. That may also happen. Now the value of n may be 1, 2, 3, 4, 5, 6, anything. Now that means this output is driving current to here as well as here, or it is sinking current from here as well as here. Now when this will drive current or source current, under which condition this output will start sourcing current? When the output is in which state? Logic 1 or logic 0?
Logic 0.
Up.
Sir.
When it is logic 0, what happens? This is on, this is off. So
Sir,
there it is sinking
Logic
current,
1.
isn't it?
Yes.
So when it is sourcing current, the current must be sourced in this manner. So that means this must remain off, this must be on. So under logic 1 condition, output is logic 1. When this is logic 1, so these are basically operating in inverse mode. That means this base emitter, individual base emitter junctions are reverse bias. When this F output is equal to 1, is it not?
Yes, sir.
So let the maximum current that this output can source is I1. Now each input current of each of these reverse bias PN junctions, let them be I2. So to how many such devices, to how many such inputs this output can be connected? Now this comes from the factor I1 by I2, the integer part of that. Say my I1 is 8 milliampere, I2 is 0.1 milliampere. A minute, I'm coming. Say the amount of maximum current that the output can source is 8 milliampere, and the amount of the reverse bias current that each PN junction requires is around 1.5 milliampere, say. So how many such PN junctions can be driven under reverse bias mode by this particular output that comes from this 8 by 1.5 factor? Is it not?
Yes, sir.
So this I1 by I2 is basically that fan out under logic 1 condition. Similarly, when this is sinking current. So there, this will be on, this will be off, and the current is flowing in this manner. If the maximum amount of current that can be synced by this particular output is I3, and when this sinking current, that means they are the corresponding PN junction at the input side, they are all sourcing current. They are basically forward biased. Is it not?
Yes, sir.
So let us assume that maximum forward bias current that can be provided by each PN junction is I4. So once again, the fan out under logic 0 condition will be given by the integer value of I3 by I4. Is it clear?
Yes, sir.
Now, the minimum of these two fan out values will be the fan out of the particular device. Why is this so? How much it is coming? You please tell me, somebody. 8 by 1.5? 6, is it so? 8 by 1.5 is how much?
So 5.33.
5.3. So that means it is 5. Okay. Now let me assume that I3 by I4 is 3 point something. So the fan out under logic 0 condition is 3 and the fan out under logic 1 condition is 5. Now what I claim is the fan out of the device will be the minimum of these two. So that means the fan out of the device should be 3. Why it is not 5? If I connect 5 such
To
input
avoid
devices,
damage.
yeah, it will get damaged when? Now, when your output is sinking, when your output is sinking, there the amount of current that needs to be synced is beyond its capability. Because 5 such input devices may start giving you that forward bias current. So that may not be accommodated by this output device. So the minimum of these two should be the fan out of the device. So in the case of TTL logic family, the noise margin is not very large. It is of the order of 0.4 volt. And the fan out is also of the order of maximum 4 to 8. Depend করছে কি টাইপের ডিভাইস তার উপর. So all such details will be available from the data sheet, from the specific maker. So the particular type of foundry that has developed this particular device, we have to consult their data sheet, and from there we'll be getting the fan out information. But the noise margin wise, that is universally true. All the devices, they are VIL max, VOL max, VIH mean, and VOH mean, they are universally decided to be those 0.0, 0.4, 0.8, 2.0 and 2.4 volts. But the fan out, they may vary a little from foundry to foundry. Anyway. By the way, কোনো confusion আছে till this point?
No, sir.
Whether what is this device? What is
MOS.
this?
The MOSFET.
MOS.
What type of MOSFET?
NMOS.
NMOS. This is basically one N-channel MOSFET. Now here, these MOS devices will be operating in switching mode. That means either they'll be on or off. Under which condition the NMOS becomes on? If the gate voltage is
Positive.
Greater threshold voltage is বেশি.
yeah. So if the gate voltage here, we will assume that to be logic 1 potential. So in case the gate potential is at the logic 1 voltage, this will be turning on. If it is 0, this will be turning off. So in case of N-channel MOSFET, if the gate input is 1, it will be on. It will be, if the gate input is 0, the switch will be off. Just the reverse is in the case of PMOS. That's why this bubble is there. This bubble indicates this is active low. The switch is active low. That means when the input gate input is logic 0, the switch is on. When the input is logic 1, the switch is off. So as the switch is active low, so that's why that bubble is present. There are many other circuit symbols of NMOS and PMOS, but in digital electronics, these two symbols are the most used ones. Okay, so we'll be also using these symbols. Now tell me what will be F in the first circuit. If A is 0, what happens to a transistor? Transistor means I am considering the MOS transistor. What happens to a transistor?
Off.
Off.
Off. So if transistor is off, what happens to the what is the current that is flowing through the resistance? Any current can flow?
No, sir.
No.
No, sir.
So as no current is flowing through the resistance, what will be the value of F?
1.
VDD. VDD or logic 1. So if A is 0, F is 1. If A is 1,
F will be
F
0.
is 0.
transistor is on. So this logic 0 potential is available at the output. So this is nothing but your A bar. Tell me what will be F here and F here.
So NOR.
Output will be 0 if any of A or B is 0 is 1. Yes, for the output to be 0, this ground potential should be available here. So that means either this path or both paths should be on.
One.
So that is possible if either A is 1, B is 1 or both A is 1. So in that case, the output will be 1. And for the output will be 0. For the output to be 1, both the switches must be off. And that is possible if both are 0. So when both the inputs are 0, then you are getting output 1. Otherwise, the output is 0. So that is nothing but the NOR operation. When both are 1, in that case output 0. When A is 1, B is 0, then also output 0. When A is 0, B is 1, then also output 0. Only when A is 0, B is 0, A plus B gives you 0, so its complement is 1. So this is nothing but the NOR operation. What about the third one?
NAND.
And
or NAND? কি বলছো?
NAND.
অনিন্দা কি বলে? NAND.
NAND.
When the for the output to be 0, this ground must come here. So for that, both must be simultaneously on. That is possible if both A and B are 1. Okay. Now, for the output to be logic 1, this path must be cut off. That means either this should be off, or this should be off, or both should be off. That means either 0 or 0 or both 0. So here the output is 0. So that is nothing but the NAND operation. Hope this is clear to everybody.
Yes, sir.
Fine. বলো এবার।
ফার্স্টটা তো A হবে।
না, এ না, এবার হচ্ছে।
Yes, sir.
আচ্ছা, yes sir, এবার নিচে আছে, yes sir.
When A is 0, this will be on, because this is PMOS. For the P channel MOSFET, for the switch to be on, the gate input must be logic 0. That's why this bubble is there, to ensure that this is active low. So when A is 0, the switch is on. As the switch is on, the VDD is coming to the output. So output is logic 1. When A is 1, the switch is off. As the switch is off, there is no influence of VDD to the output. Instead, this ground terminal or ground potential goes to the output through this path. Okay, so A0 output 1, A1 output 0. So this is nothing but your A bar. Second one.
NAND.
দেখি আর কি বলে।
It's a NAND.
It's a NAND.
For the output to be 1, either this to be on or this to be on. তাহলে corresponding path দিয়ে আমি I'll be getting VDD at the output, or both to be on. So 0 0 0 1 1 0, এই তিনটে কেসেই আউটপুট হচ্ছে 1. When output is 0, that is possible only when both are simultaneously off. because that will only ensure that VDD is totally disconnected from the output. To ensure that, I must have both the switches to be off, and for one P switch to be off, the corresponding gate input must be 0. So, sorry, must be 1. So, for one input combination, the output will be 0. For others, the output will be 1. So, this is nothing but your NAND.
So NOR.
Yeah. For the output to be 1, I need both the switches to be on, because the switches are in series combination. So to ensure that both A as well as B must be logic 0. So when the inputs are 0, 0, then only the output is 1. Otherwise, either of the two switches or both the switches will be off. So the ground potential will be available at the output. So for 0, 0 input combination only, the output is 1. Otherwise, the output is 0. So that is nothing but the NOR operation. So using NMOS, I have realized inverter, NAND, and NOR. Similarly, using PMOS, I have also realized inverter, NAND, and NOR. Now the significance is that we know that NAND and NOR, they are called
Universal logic gates.
Universal logic.
That means using only NAND gate, I can realize any logic circuit. Using only NOR gate, I can realize any logic circuit. So if some function is given to you, that can be readily implemented using NMOS or PMOS, with which MOS family you want me to realize this? I am going to implement this with a particular logic family, particular NMOS or PMOS logic family. Which one of them you will be prescribing for me?
NMOS.
NMOS. Fine. Now here you find that 3 inverters are required. One to realize A bar, the other to realize C bar, the other to realize B bar. Achha, by the way, this is in SOP or POS?
SOP.
SOP. So you have to go for the NAND and AND operation. So A. Okay. This can be rewritten of this form, is it not?
Yes, sir.
So now I require 3 inverters. Then I have to go use one 2-input NAND gate and another 3-input NAND gate. NAND means series combination in the case of NMOS. Here I require A bar, C bar, bar. So that means A bar should be one input and C bar should be other input. Then I have to go for one 3-input NAND gate. The output should be A, B bar, C bar. So one input is A, second input is B bar, the third input is C. Then I require the final two input NAND gate. So that's the serialization. Is it clear?
Yes.
Fine. If anybody is having any doubt on this, please tell me.
No, sir.
Don't go for wiring the two terminals. Like don't go for wiring like this. That will make the circuit clumsy. Just simply write the node voltage names, and it is implied that as ever is written here and ever is written here, these two terminals are connected. So there is no explicit requirement of wiring the two nodes, provided you have given the names properly. That's all. Okay. Fine. I think you should be able to realize this using PMOS, and let me have that as your home task. Realize this particular circuit using PMOS. I think you should be able to do it.
Yes, sir.
In Tuesday, I'll take. In fact, I need just 1 hour extra. One more hour lecture will be able to finish my topics. So should I do it on a Tuesday or on the Thursday itself?
So you can do on Tuesday.
Okay, fine. So before the demonstration, I'll go for this lecture of 1 hour, and then I'll go for the demonstration. And tomorrow from 11, one optional demonstration will be there. So whoever is want to present that your assignments, you can do it.
Okay, sir.
Mansoor,
Present, sir.
Ashish Patro, absent. Boyhav Shah, absent. Jogesh Tiwari, absent. Mustafa Kamal,
Present, sir.
Sublin Singh, absent. Shikha Shah, absent. Sawaj Parvez, ওদের বিয়ে বাড়ি গেছে না?
হ্যাঁ স্যার বিয়ে বাড়ি গেছে।
এমন ছবি দিচ্ছে। সুরজ মোহন সোরেন, অ্যাবসেন্ট। ব্রতিন ঘোষ, অ্যাবসেন্ট। সন্দীপর্ণ, অ্যাবসেন্ট। রিয়ন সামন্ত is absent. Ankit,
Present, sir.
Ankit, are you still in Bihar or have you come to Kolkata?
Sir, in Bihar only.
No. Have you got any hostel or accommodation in near the Salt Lake campus?
No, sir, I haven't got hostel.
Okay. Saurabh Sen, absent. Sangram Shah, Sagar Chaudhary,
Yes, sir. Present, sir.
Biplab Sarkar, absent. Moinak Das, absent. Ayushman Brahmo, absent. Shuddha Satya, absent. Oniket Ghosh,
Present, sir.
Udbhash, absent. Somojit Acharya, absent. Arnab Sheth, present. Nilargho, absent. Parvez Mollik, present. Ashraf Hossain,
Present, sir.
Srinjoy, Rashid Asgar absent, Aryan Sardar absent, Onindita present.
স্যার আমার একটা জিনিস বলার ছিল, আমি অ্যাটেন্ডেন্সের পর তারপরে
হ্যাঁ ঠিক আছে।
Yes.
সৌরভ মন্ডল absent, প্রসেনজিৎ মন্ডল absent, সোহম কাঞ্জি absent, শিল্পা মন্ডল absent, অনির্বাণ নস্কর absent, জয়দীপ present, শুভজিৎ মন্ডল
Present, sir.
মৃদুল absent, মৃত্যুঞ্জয় রাও absent, সূর্য কুমার মাঝি absent, Nishant Patel, I think he has left. Absent, Gulshan Poddar absent, Obhirup Kobiraj,
Present, sir.
Ornik absent, Orijit Paik absent, Shomik Chaudhary,
Present, sir.
Rajdeep Kundu,
Present, sir.
Obhirup Saha absent, Shourjo Dotto absent, Sitoma Ghosh absent, Himanish Pal absent, Himangshu Ranjan absent, Biplab Mahapatro absent, Joyita Roy absent, Saptasho absent, Orpon Gayan absent, Obhik Pal absent, Tomal Khada।
Yes, sir.
যখন ডাকলাম তখন পেলাম না কেন? প্রসেনজিৎ দরিপা,
Present, sir.
নাসির উদ্দিন অ্যাবসেন্ট। ওকে, হ্যাঁ অনিন্দা বল, বাকিরা বেরিয়ে যেতে পারো, থাকলে থাকতেও পারো।